Hi guys, Audrey here. So in this video, we're going to try to answer the question, how can we determine if a series a sub n, or sum n equals 1 to infinity of a sub n, converges or diverges if the test for divergence fails? In other words, if the limit as n goes to infinity of a sub n equals to 0. So this is actually a really challenging question to answer, and we're going to come up with quite a few different ways to answer it. The first tool that we're going to have in our toolbox for figuring this out, though, is something called partial sums. Partial sums. And so a partial sum is when instead of going all the way up to infinity, we just go up to some finite number. And every single series will actually have an infinite number of partial sums. So let's get that definition down and see what I mean. So, definition. We say that the nth partial sum of a series is just the sum of the first n terms. Is the sum of the first in terms. So if we were to look at this in terms of an actual series, what this would look like is I could have, for example, the series n equals 1 to infinity of a sub n. Then s sub 1, so this is our notation that we use for partial sums. We do s sub 1. S sub 1 would be equal to the sum n equals 1 to 1 of a sub n, which means that we're just summing up the first term. So this right here is what's called the first partial sum. First partial sum. The second partial sum, which would be s sub 2, is the sum n equals 1 to 2 of a sub n, which is a sub 1 plus a sub 2. So it's the sum of the first two terms. So you can see what I mean by saying that every series has an infinite number of partial sums, because I could then go to 3, 4, 5. So with every series, we have these partial sums. So this is my second partial sum. Then s sub 3, when I add up the first three terms, would be my third partial sum. And so on and so forth. So I could then go down and say, well, then s sub n, the sum from n equals 1, actually, we're going to do this with a capital N, s sub capital N, the sum of n equals 1 to n of a sub n would be the sum of my first n term. So a sub 1 plus a sub 2 plus dot, 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 plus a sub n. And that right there is what's called my nth partial sum. And so if I take all of these partial sums, I can actually create a sequence called the sequence of partial sums. So the sequence of partial sums, actually we'll do this as a definition as well. The sequence of partial sums the sequence of partial sums is the infinite sequence made up of the partial sums of a series. Sums of a series. And for this sequence, we use the notation s sub n. So here my S sub n would be the sequence that's made up of S sub 1, S sub 2, S sub 3, then S sub n, and so on and so forth forever. The n plus 1th term, the n plus 2nd, the n plus 3rd. So as we add more and more, we're going up in our sequence of partial sums. So now, how is this sequence of partial sums useful? Well, if I go back and look at these partial sums, that first partial sum, it's a little bit weird to think about it, but I can think of it as an approximation for the actual value of the series. It's a bad approximation because it's only one term instead of all infinity of the terms, but it's still an approximation of the series. So I'm thinking of this as a bad approximation of the series. But then with that said, my second partial sum, when I add another number, would still probably be a bad approximation of the series, but it would be a better approximation of the series because I've added more of the numbers in my series together. So this would be a better approximation of the value of the series. And then if I'm adding 3, the infinite number of terms together, instead of just 2, well, I'm getting even closer to the actual value. So this third partial sum is yet an even better approximation of the series. And as I add more and more numbers, then I'm going to be getting closer and closer to the actual value of the series. More numbers. So in other words, as my S sub n gets bigger and bigger and bigger, I'm getting closer to the actual value. So in other words, I can think of this sequence of partial sums right here, this sequence of partial sums, as a sequence of approximations of the value of the series. So in other words, think of the sequence of partial sums as a sequence of approximations for the series, where as n gets bigger, the approximation gets better. Okay, so with that in mind, what do you think is happening as n goes to infinity to the sequence of my partial sums? In other words, what do you think happens as we take the limit as n approaches infinity of S sub n? So in other words, we're saying what's happening to the values of that sequence as n gets bigger and bigger and bigger? Well, we just said that we can think of this sequence as a sequence of approximations, whereas n gets bigger and bigger and bigger, the approximation gets better and better and better and closer and closer and closer to the actual value of the series. So in other words, by looking at this limit, we see what's actually happening to the series. So we see what's happening to the series itself. And so from this, we have this nice theorem. Theorem that says if, oops, I don't want to do that in pink. If S sub n is the sequence of partial sums of a series A sub n, then if the limit as n goes to infinity, infinity of S sub n goes to L and exists. So in other words, we're saying these values are getting closer and closer and closer to some actual number, like maybe 8, then the series converges to 8. So then this converges to L. If, however, what we see is that these numbers are just getting bigger and bigger and bigger without bound, or maybe smaller and smaller and smaller, infinitely smaller without bounds, or maybe they're just like going back and forth and never going anywhere, like 3 minus 1 plus 3 minus 1 plus 3 minus 1 plus 3 minus 1, where they're never actually going anywhere, then we're never getting anywhere. And so that would mean that my series diverges. So if the limit as n goes to infinity of S sub n goes to infinity or negative infinity or does not exist, then the series n equals 1 to infinity of A sub n diverges. And this is a super, super, super important result. It's telling us that we can just look at the sequence of partial sums in order to determine whether or not a series converges or diverges. Okay, so just to make sure that we really understand this, let's do this with an actual concrete example. So earlier today, we looked at, or actually in another video rather, we looked at the sum n equals 1 to infinity, oops, of 1 over 2 to the power of n. And we actually kind of made the conclusion that this probably converges to 1. So let's look at the partial sums and see if what we've just done here makes sense in terms of that. So my S sub 1 here would be the sum from n equals 1 to 1 of 1/2 to the n, which would just be 1/2. My S sub 2 would be the sum from n equals 1 to 2 of 1/2 to the n, which would be 1/2 plus 1/4, which would be 3/4. Then S sub 3, we're just adding up the first 3 terms, 1 over 2 to the n, and we get 7 over 8. So I'm just going to do one more here. S sub 4, n equals 1 to 4, 1 over 2 to the n would be 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. And that's going to give me 15 over 16. So if I look at my sequence of partial sums here, sequence of partial sums, would be S sub n, and that's going to be 1/2, 3/4, 7/8, 15/16, and so on and so forth forever. So what should be happening if we rewrite earlier is that these numbers should be getting closer and closer to 1. As I add another term, I'm getting closer and closer to 1. And we can see that this is actually happening here. We start with 1/4, but as my partial sums move up, these numbers do indeed seem to be getting closer and closer to 1. Numbers seem to be getting closer and closer to 1. So from this is really not a rigorous way to do this at all, and we're definitely not going to do it this way in the future. This is really just to kind of understand the partial sums. From this, we're going to conclude that this does indeed converge to 1. But like I said, this is not really a rigorous way to do this. It's kind of like looking at it and being like, oh, look, those numbers seem like they're getting closer to 1. But in math, seems like is never really a good way to show something. So the question is then, how can I find S sub n itself? I've got my sequence of partial sums. We've talked a little bit about coming up with general terms for sequences by looking at the terms. But the problem is that a lot of times those sequences of partial sums, the patterns are really, really challenging. And it's actually really hard to come up with the S sub n for the sequence of partial sums. So over the next few classes, we're going to be looking at ways to do that and looking at ways to determine whether or not series converge or diverge, even if we can't do that. So in the meantime, we're going to leave this at this. We kind of understand what a partial sum is, and we're just going to do some examples when we're given S sub n. So we'll make a little note. Unfortunately, it is often really challenging to find S sub n. So over the next few classes, we'll look at this. In the meantime, like I said, we're going to do an example where we're actually given S sub n and just kind of see how this works. So let S sub n equals to 8 minus n over 4 to the n be the sequence of partial sums for the series. N equals 1 to infinity of a sub n. And the first question we're going to ask here is, does the series converge or diverge? Does the sum n equals 1 to infinity of a sub n converge or diverge? Okay, so what we've just seen is that in order to answer this question, I can just look at the limit as n goes to infinity of S sub n. So the limit as n goes to infinity of 8 minus n over 4 to the n. Well, here we can see that this 4 to the n is growing more quickly than n. And so we've proven that in this particular case, that's going to be going to 0. I could apply L'Hopital's rule one time, but this growth rate chart allows me to see that this is actually just 8 minus 0 and equals to 8. So what this tells me is that the sequence of partial sums converges to 8, and therefore the series itself converges to 8. The sequence of partial sums converges to 8, and therefore the series converges to 8. Okay, next question is, what is the limit as n approaches infinity of a sub n. Well, notice I don't have a sub n. In a second, we're going to see that we can actually pretty easily find a sub n, but we don't need to do that to answer this question. What is the limit as n goes to infinity of a sub n? This can be answered just by using the test for divergence. The sum of n equals 1 to infinity of a sub n converges. If it converges, then we know that the limit of a sub n has to be 0. Because if it were not 0, then the test for divergence would have told me that it diverges. Remember, the test for divergence says if the limit doesn't equal 0, it diverges. If it does equal 0, do something else. So here it converges, which means that by the test for divergence, that limit would have to be 0. If it diverges, then we just genuinely have no clue what that limit is. So converges. So by the test for divergence, the limit as n approaches infinity of a sub n is equal to 0. Next question. I want to write out the first two partial sums. Write out the first two partial sums. And then we're going to find a sub 1 and a sub 2. Okay, so my s sub 1 here, we know is the sum of n equals 1 to 1 of a sub n, which is just equal to a sub 1. And my s sub 2 is the sum n equals 1 to 2 of a sub n, which is a sub 1 plus a sub 2. Well, I also know what s sub n is, so I can actually just plug in to find these things. So we're plugging into 8 minus n over 4 to the n. So s sub 1 is equal to 8 minus 1 over 4 to the 1. So that's 8 minus 1/4, which I'm actually just going to leave like that for a second. And then my s sub 2 would be 8 minus 2 over 4 squared. So that's 8 minus 2 over 16. So that's actually 8 minus 1 over 8. So this is my s sub 1, my first partial sum. And this is my s sub 2, my second partial sum. And now I want to use this to find a sub 1 and a sub 2. Well, I know that a sub 1 is the same thing as my first partial sum. We can see that on the left here. S sub 1 is equal to a sub 1. So then this tells me that a sub 1 is equal to 8 minus 1/4. But we can also see over here that a sub 1 plus a sub 2 is my second partial sum. So that is equal to 8 minus 1 over 8. But because I know a sub 1, I can just subtract it from a sub 2 in order to get a sub 2. I mean, from s sub 2 in order to get a sub 2. So in other words, what we're doing here, just kind of make this clear, we're saying that a sub 1 plus a sub 2 is equal to s sub 2. So a sub 2 is equal to s sub 2 minus a sub 1. So then over here, I can say that a sub 2 is equal to 8 minus 1 over 8 minus 8 minus 1 over 4. So I actually get that a sub 2 is equal to negative 1 over 8 plus 1 over 4. And I'm going to leave it like that, even though I could easily add these fractions together. So that would give me 2 minus 1. That would actually give me 1/8. So that right there is my a sub 2, which I was able to find by thinking about the fact that a sub 2 is equal to s sub 2 minus a sub 1. Okay, so our last question that we're going to do here is find a sub n. Okay, well, to find a sub n, we're going to actually think about this thing that we have right here, that a sub 2 is equal to s sub 2 minus a sub 1. So we can actually conclude here that a sub n, so if I'm looking at this, a sub n is going to be equal to s sub n minus s sub n minus 1. This a sub 1 right here is s sub 1. So this is like s sub 2 minus s sub 1. And that actually continues on forever. So a sub n itself will just be s sub n minus s sub n minus 1. So here my s sub n is 8 minus n over 4 to the n, which means that s sub n minus 1 is 8 minus n minus 1 over 4 to the n minus 1. Okay, I'm going to simplify this thing on this s sub n minus 1 though, because I know that 4, oops, I'll do this below actually, 4 to the n minus 1, excuse me, 4 to the n minus 1 is equal to 4 to the n, 4 to the minus 1, which is 4 to the n times 1/4. So this is actually 8 minus 4 times n minus 1 over 4 to the n. And the reason I've done this is because now my s sub n and s sub n minus 1, those denominators are the same. So I can say that a sub n is equal to s sub n minus s sub n minus 1. Those 8s are going to cancel out there. And I end up with minus n over 4 to the n plus 4n minus 4 over 4 to the n. And I can see that this is equal to 3n minus 4 over 4 to the n. And that is my a sub n. So basically what we've just seen is that the series n equals 1 to infinity of 3n minus 4 over 4 to the n converges to 8. And the limit of the series, the sequence that's associated with that series, the limit as n goes to infinity of 3n minus 4 over 4 to the n, we can now see definitely does equal 0, like we concluded up here. All right, so that's it for partial sums. They can be a little bit confusing the first time you see them, so try to wrap your minds around this. Next class, we're going to do a little bit more with them.